Okay, so today's lesson is going to be on decomposition. So we are using our reference tables, the decomposition section, and you can see I have rewritten our reference tables on this particular worksheet. We have 6 different types of decomposition reactions based upon our reference tables. A binary compound can decompose, meaning break apart, into its 2 individual elements. M is a metal. So a metallic, root word there, metal, it has a metal in it with a carbonate, is going to make a metal oxide plus carbon dioxide. If we have a metallic hydrogen carbonate, that's going to make a metallic carbonate plus water plus carbon dioxide. If we have a metallic hydroxide, that makes a metal oxide plus water. A metallic chlorate is going to make a metal chloride plus water. And then an acid is going to make a non-metal oxide plus water. All right, what do we notice about a decomposition reaction? All of these decomposition reactions have a single reactant. So you can determine a decomposition reaction pretty easily. If it has one reactant, then it is a decomposition. So let's look here. Sodium oxide. So we're going to write sodium oxide. Now, what type is this? I have 2 elements, but none of them fall into the other categories. It is not an acid, so it has to be a binary compound. So I have 2 elements, which is a binary compound. So A is the sodium, B is the oxide in this particular example. So this is a type A. We are going to break down into our 2 individual elements. Na plus O. Remember, O is diatomic when by itself, oxygen. And oxygen at room temperature is a gas. And then we simply have to balance. So when we balance our equation here, we get a 2 in front of the sodium oxide and a 2 in front of the sodium. I'm sorry, a 4. That should be a 4 in front of the sodium. All right, magnesium carbonate. Magnesium carbonate. So this is going to be a type B. I have a metal, the magnesium, plus I have a carbonate. So this is a type B reaction. So what do my reference tables tell me is going to happen? A metal oxide plus a carbon dioxide. So my metal here is magnesium. And when I swap and drop magnesium and oxide, I get MgO plus carbon dioxide. And when I look here, this happens to balance out. I have 3 oxygens on the left, 2 plus 1 is 3 oxygens, and my magnesium and carbon both have 1. A potassium hydrogen carbonate. All right, so that's going to be a type C. Potassium is my metal. I have a hydrogen carbonate. So I'm going to make a potassium carbonate plus liquid water plus gaseous carbon dioxide. So we said it's a type C. Potassium hydrogen carbonate. All right, and it is going to make potassium carbonate. And again, remember when we swap and drop K plus and CO3 2 minus, swap and drop to K2CO3 plus liquid water and gaseous carbon dioxide. And then we have to balance. I have 2 hydrogens on the right side, the product, so I'm going to put a 2 in front. I just said hydrogen. I'm sorry. I have 2 potassiums on the product side. So I need 2 potassiums on the reactant side. And when I put a 2 in front, that ends up balancing everything else as well. 1 hydrogen times 2 is 2, which I have on the product side. 3 times 2 is 6 oxygens. I have 3 plus 1 is 4 plus 2 is 6. All right, let's check out potassium hydroxide. This is going to be a type D. So I'm going to have my potassium is the metal. Here's my hydroxide. I'm going to make potassium oxide and water. Let me start over. Calcium hydroxide. Calcium is my metal, so I'm going to make calcium oxide plus water. I'm sorry for that confusion there. Calcium hydroxide. So when I write out my formula, calcium hydroxide, now this is going to be a type D reaction. My reference tables tell me to make a metal oxide, so that's calcium oxide plus water. And when I look here, I have 1 oxygen times 2 is 2. There's 2 oxygens. 1 hydrogen times 2 is 2. There's 2 hydrogens, and I have 1 calcium on each side. So this balances out. All right, lithium chlorate. Lithium chlorate is a type E reaction. Now, you'll be provided your reference table, so you don't have to memorize all of this. All of this is on your reference tables, and you can refer back to your reference tables on all of our assessments. You'll always get a copy of those reference tables. So when I write lithium chlorate, LiClO3, what do my reference tables tell me? A metal chloride. So in this case, the metal is lithium. So that's going to be lithium chloride plus O2. And oxygen is a gas at room temperature. So we'll go ahead and mark that. We don't necessarily have enough information to know what everything is in terms of their states of matter, whether it's a solid, a liquid, a gas, or aqueous. But what we do know, we can mark. Now we need to balance. All right, and so when I balance this, if I put a 2 in front of the lithiums, that should balance me out. I have 2 lithiums on the left and 2 on the right. 2 chlorines on the left. 1 times 2 is 2. 1 times 2 is 2 chlorines. And I have 3 times 2 is 6 oxygens. So on the right side, I have 2. I just have to put a 3 in front there, and that works out. All right, our final type is an acid. An acid decomposes into a nonmetal oxide plus water. Now, the acid, what do we notice here? If we come up here to a synthesis reaction, a nonmetal oxide plus water gives us an acid. So synthesis type C and decomposition type F are actually opposites. Synthesis type B, as in boy, a metal oxide plus water, forms a base. We know a base is hydroxide. Look at this. A decomposition type D is a metal hydroxide, decomposes into a metal oxide plus water. So a synthesis type B is the opposite of a decomposition type D. Because remember, a synthesis reaction forms one reactant. So let's look here. Sulfurous acid. And this is a type F. All right, so we're going to do the opposite process that we did in the synthesis. So we are going to take our polyatomic ion sulfite, And we're going to remove an oxygen because we need that oxygen to come over to water. So H2 plus an oxygen forms the water. And if I remove an oxygen from SO3, what does that leave me? SO2.